Hello, everybody, and welcome. I hope everyone's having a good start to their day. Thank you for joining us for today's edition of our 1-hour Vic Gardner web seminar. Today's topic is control of color, gloss, and grain. So if you are hearing my voice right now, you've passed the test and managed to connect to the web seminar's audio. If you are not currently hearing my voice, there's nothing I can do to help you audibly. Hopefully you will be able to figure it out from this slide here, which we will leave up for just a few seconds. Okay, your speaker today is myself, Corey Cohen, Application Specialist with Vic Gardner USA for the past 10 years now, and I specialize in customer education and technical training. Just some general announcements before we begin. You have all been muted, so you can go ahead and sip your coffee, talk to your cats, whatever you like to do, and nobody can hear you. You will only be hearing my voice for the duration of this web seminar. If you have any questions I have not answered by the end of the presentation, please enter them into the chat function. We will have some time to answer some questions following the presentation. And yes, a PDF version of this presentation will be sent to everyone following the presentation by email. I'd also like to mention that the web seminar is being recorded, and you will have access to the recorded version of this presentation via the same page you used, the web page you used to sign up for this web seminar on our BYK Instruments website. That should be available for about a month or so following today. So here we go, control of color, gloss, and grain. Let's begin. So today's agenda includes what do we really see, how to measure grain size and depth, how to judge the reflection behavior of very low gloss surfaces, how the perception of depth is influenced by the reflectivity of the surface, hills and valleys, and can now be objectively evaluated with a measure of contrast. And we'll talk about some typical practical examples covering auto interior, coarse paint surfaces, and fine textures. So when it comes to controlling the look of a product, one of the most difficult things to control for is the texture. So we have traditional measurement methods like color and gloss, but they can't tell us much about the look of the structure of a surface. And so we need new measurement technologies to be able to evaluate and control for these things. So this is why we provide a combination of several different measurement techniques in one instrument. That instrument is our new Spectro 2 Profiler instrument, which measures color and gloss, as well as aspects of surface structure. So, beginning with the color measurement. This is, of course, an important aspect of the visual impression, something, of course, we want to measure. And so pictured here, we have a 45-0 geometry spectrophotometer. And we can see from the side view diagram here on the left, this type of meter uses a directional light source, which hits the surface being measured at a 45-degree angle. And the detector is positioned normal to the surface or at the 0-degree angle, hence the 45-0 geometry. And if we look at the top view, we can see that there are actually multiple light sources spaced all around that measurement spot. And all this light coming from all around is all going to hit the surface at a 45-degree angle, but it's going to surround the measurement spot in what is essentially a cone of light. And this is what we refer to as circumferential illumination. It just means that the spectrophotometer can be oriented any way on the surface. You can, take a measurement, turn it 90 degrees, and take another measurement. You should get consistent measurements no matter which way you turn it. So by the way, circumferential illumination, that's what the C stands for in 45C0. That's kind of a new notation, but 45 is for the angle of the light source, C is for circumferential, 0 is the angle of the detector. So, in addition to color measurement, we have gloss included in this instrument as well. This is, of course, a long-standing specification for things like matte car interiors. So here we have pictured a diagram of a 60-degree gloss meter. And the geometry and the specifications for this type of meter are established by international standards. So we have a light source positioned at 60 degrees off the normal, and a detector positioned at the opposite 60-degree angle in order to measure the specular reflection. So just as sort of a review real quick for those of you who may not be familiar with terms like specular, when light hits a surface, some of that light is going to reflect off at the opposite angle, that specular angle, which is where the detector is positioned in this diagram. And some of that light, when it hits the surface, is going to be diffused, just meaning it reflects off in all directions. It's deviated to all directions rather than reflecting right off at that specular angle. So glossy surfaces have a high specular reflection and a low diffuse reflection, and low gloss surfaces have a high diffuse reflection and a low specular reflection. So the gloss meter's job is to measure the specular reflection off the surface, which is a direct indicator of how glossy the surface will look. So higher specular reflection equals glossier surface. Now, gloss measurement works well mostly for very smooth, flat surfaces, but there's a major issue when it comes to textured surfaces, and you can see what that is when you look at that sort of diagram to the right. The fact is that structures in the surface are going to cause these shadows, and it's going to cause some of that light to be reflected away from the detector, even when it's not due to that light being diffused. It's not due to the surface being low gloss, it's just due to structures in the surface reflecting that light off at different angles. So this is going to sort of falsify our gloss results, or give us results that don't match well with the visual. And so we're not really getting a true measure of how glossy the surface actually looks. And more than that, if you turn the meter to a different orientation, you're likely to get different results on a textured surface. The gloss meter doesn't have circumferential illumination like the color meter does, and so the orientation of the meter is going to have an effect on the measured gloss, especially on textured surfaces. So we need to find another way to measure these textured surfaces, to measure the gloss, the reflectivity of these textured surfaces. So this is where the 2D reflectivity measurement comes in. So with this measurement, the light source is in line with the camera. So you can see from this little diagram towards the left that the illumination is coming from the side, and then it passes through this beam splitter, which is going to redirect it down to the surface, and then you have a camera that's going to take a picture of that. And so that way the light beam is in line with the camera, and the light source doesn't have to be blocking the camera since it's coming in from the side. And so this picture is taken under this illumination condition, and then that picture is analyzed pixel by pixel. So with 2D reflectivity, we actually get spatially resolved reflectivity measurements, which basically just means an image. So here we have a reflectivity map of a powder-coated surface. The dark areas are areas of low reflectivity, and the lighter areas have higher reflectivity. And each pixel, each individual pixel is assigned a reflectivity value. And the measurement is referenced to a light trap for the dark calibration, and also to a matte, a low gloss white tile for the light calibration, and that tile has a reflectivity of 2500. So the overall range of reflectivity actually goes up to 500,000 units. But here the average reflectivity, so each a reflectivity value is assigned to each pixel. All of those reflectivity values are average, and you get an average reflectivity value, which for this image right here, this surface being measured, is 11,572. So here we have those two methods side by side, the traditional gloss measurement on the left, where the light's hitting the surface at an angle, and the 2D reflectivity measurement on the right, where the light is in line with the camera, which eliminates the casting of shadows. Also remember that the reflectivity measurement, unlike the gloss measurement, is spatially resolved, which just means that we're measuring the reflectivity of a large number of spots on this surface individually, as opposed to the gloss measurement, which just sort of averages the gloss over the area that that light beam is covering. Okay, so we have color, we have gloss, we have 2D reflectivity. And to round out this set of measurements, we have also the 3D topography measurements. And this is done by taking an image of the surface under 4 different illumination conditions. So the surface is illuminated from 4 different directions, and a picture is taken under each lighting condition. And then based on the curvature that it's getting from each lighting condition, the curvature revealed by that illumination, a height map is able to be calculated. So whereas the 2D reflectivity measurement is measuring how much light is being reflected by the surface, the purpose of the 3D measurement is to map the actual shape, the actual height or topography of the surface. And so here we have a diagram showing the setup of the 3D topography measurement. So in the side view, we see that the illumination is coming from 60 degrees off the normal. And by looking at the top view, we see that the 4 light sources are positioned at 90 degrees each other with the camera at the center. And the result of this measurement is a height map, as we can see right. The height map is color-coded so that the yellow, the light orange portions indicate the highest elevation, and the purple portions indicate the lowest. So here we have our 4 measurement techniques: a color meter with a 45C0 geometry. We have 60-degree gloss measurement, 2D reflectivity, and 3D topography. And so for textured or structured surfaces, this collection of measurement techniques, this collection of evaluation methods, will provide a complete analysis of the appearance of the surface. Okay, so now that we've had sort of an overview of these different measurement techniques and how they work, we're going to get into a little bit more in-depth analysis of particular types of surfaces and how these measurements we discussed are actually quantified, how they can actually be useful to you. So in the research phase for this technology, we found that different types of surfaces, different types of textures require different types of analysis. So we've come up with these algorithms for certain types of materials. So we have the coarse paint algorithm, and this is meant for glossy, coarse paint, such as powder coatings. We have the Leatherlike algorithm, and that's for materials that are meant to mimic the look of leather, like structured vinyl that you might see in a car interior or maybe on vinyl upholstery. And we also have the fine algorithm, which is good for fine structured paints and plastics as well. So we'll begin by exploring the Leatherlike algorithm. So when we look at different samples with a leather-like grain, what do we see? Well, color, gloss, those are things that are going to jump out to us, but some of the things that we're going to see are the grain size and the height. And these may not be things that you notice specifically or notice individually unless you're really looking for them, but they are certainly going to have an influence on our overall visual impression of the surface. So in order to evaluate the surface, we really need to be able to quantify these things, the grain size and the height. And so we do that by measuring the mean cell size, CS, as well as the mean cell amplitude, CA. Here we have an image of our 3D topography measurement of a surface, of a structured surface. And the image has been segmented into high spots, which are orange, low spots, which are purple. And we do this using what we call the drop of water principle. So you can imagine this like rain falling on the surface, and water collects in the low spots and creates these quote-unquote around these high spots. And these rivers define closed cells. So this is referred to as watershed segmentation. So here we have another topography image with the raw image on the left and that watershed segmentation done on the right. And now once these cells have been segmented in this way, the size of the individual cells can be calculated, as well as the mean cell size, CS. And I'd also like to mention that only the cells that are completely surrounded, meaning the cells that are completely inside the camera image, are going to be counted. So these cells here on the edge, where you can't see where they end, they're not going to be counted in the calculation. So here we have the mean cell size measured for the 3 leather-like samples we saw before. And we see the watershed segmentation in each of these images. And we can see from both the images and the numbers that the sample 2 has the largest average cell size, while sample 3 has the smallest. Here we have pictured a master panel with 5 different sections, and each of these sections has a different depth, or at least a different apparent depth. And you can see that the section at the top marked 100%, and that has the deepest grain, and the depth decreases as we move down the panel to those lower percentages. And so what we'd like to determine here is the mean cell amplitude. So again, we have our topographical image, which again has been segmented using the watershed method, and the amplitude of a single cell is calculated as the maximum height of the cell. And that's indicated by the red X's in this image to the right. And so we take that and subtract the minimum height of the valley surrounding the cell, the low point, and those are indicated by the blue plus signs. So it's essentially the height difference between the highest local point and the lowest local point. And you can see what I mean from this drawing here at the bottom. And so the mean cell amplitude, CA, is of course the average amplitude of all the cells within the image. Here we have the measured mean cell amplitude for each section of this panel. And we can see this provides pretty good correlation with the visual grain depth. And I'd like to point out here that the depth is given in units of perceived microns. Yes, perceived microns. We're actually measuring perceived amplitude rather than actual amplitude. And this is because the perceived amplitude is actually based on the amplitude being based on perception actually correlates better with what we see visually than the actual amplitude does. And so the differences in perceived amplitude versus actual amplitude have mostly to do with the color and the reflectivity of the surface. Different colored surfaces cause us to perceive the depth of the grain differently. And so that's why we use perceived amplitude rather than actual amplitude, because we want to measure what we see visually rather than what's actually going on, because that's going to help us correlate our measurements better with the visual. So we'll get a little more into exactly what's going on there a bit later. So here we have the set of measured values when using the Leatherlike algorithm. And in this table, we can see the LAB values for each of these samples as measured with the 45-0 spectrophotometer built into the profiler instrument. And those LAB values, they're all fairly close to each other, probably within a delta E of about 0.5 or so, certainly less than 1. So that's a fairly small color difference, but we know these samples do look somewhat different visually. And so if we look at the reflectivity values and the cell size and cell amplitude values, we can see where those differences lie. So it's the difference in the structure rather than the difference in the color that's causing those visual differences. So here we have 6 different samples of the same texture but different color. Okay, and so we can see the L values, measured L values of each of these samples graphed here to the right. And we can see that the sample lightness increases as we go. So the black sample is the darkest and the sample is the lightest. And despite the fact that all these samples have the same texture, the same physical texture, we're perceiving greater depth on the darker samples. The black, the blue, they look deeper, they look more textured than the gray and the beige because of the difference in the lightness values. And the reason for that is because when you get light hitting these areas between the texture, these low areas, you're going to get these interreflections that lighten up the shaded areas of the surface. So this effect strongly depends on the color, because the brighter the surface is, the lighter the surface is, the more of these reflections you're going to get. And this is going to cause a difference in the way we see the surface. So the interreflections affect the human visual perception as well as the image acquisition with the camera system. So the camera system is seeing things as we see things. So in both cases, the topography details of the surface vanish with increasing surface brightness. And so the lighter colors look more shallow to us. And so that's why we speak of perceived height, perceived amplitude. And we give these values in perceived units, perceived height scales. Okay, so here we have another 4 samples. And the texture size here, the texture size is more or less the same, and yet they still look visually different despite having more or less the same topography. And so this is where the reflectivity comes in. The hills and the valleys of these surfaces have different reflectivity from sample to sample, and this is what's causing us to see the visual differences in the appearance. So in order to control for this, we need to determine the reflectivity contrast, RC. So this type of measurement combines the 3D topography data with the 2D reflectivity data, which we can do because it's the same camera system. The same camera took both sets of pictures. So the pixel by pixel reflectivity data can be overlaid on top of the topography image. So now we can determine the reflectivity of the hills and the reflectivity of the valleys. We can combine those values to calculate the reflectivity contrast using this equation right here. So reflectivity contrast is just the difference between the reflectivity of the hills and the reflectivity of the valleys divided by the sum. And if we look at the picture of those same 4 samples to the right, we can see, so to me, samples 1 and 3 appear to have the most depth or the most texture. Sample 4 has a little less, and sample 2 appears the most shallow. And if we look at those RC numbers, the reflectivity contrast numbers, we see that this data correlates with this visual impression pretty well. So the higher the difference in the reflectivity between the high points and the low points, the higher the perceived depth of the grain. And this is another part of the reason why we use mean cell amplitude or perceived amplitude rather than the actual amplitude, because we want the measurements to reflect what we see visually. So here we're comparing those reflectivity measurements with gloss measurements. And we can see why we need reflectivity, why gloss isn't good enough to differentiate between these samples. So you can see the reflectivity data, it's much more detailed, much more precise for this type of material. So the reflectivity data is showing much more differentiation between these samples. And as we've seen, this does correlate well with what we're seeing visually, whereas that gloss measurement alone isn't really capable of differentiating between these samples. Okay, we've covered the Leatherlike algorithm. Now let's delve into the Coarse paint algorithm. So here we have 4 powder-coated samples now, 4 glossy powder-coated samples. And again, we can see some variation in these samples. Sample 1, I would say, has a somewhat fine texture, at least relative to the others, and then the texture gets coarser or rougher as the sample number increases. So when we say coarser, when we say rougher, what we're really saying is that the cell size is larger. And so in order to properly quantify this effect, to properly quantify the appearance of these samples, we need to be able to measure the mean cell size. So again, we rely on the Watershed segmentation method, which allows us to calculate the size of each cell within the image and then average them to arrive at the mean cell size, CS. And now we've graphed the mean cell size for each sample, and we can see that the CS value, that mean cell size value, increases from sample to sample, and so too does the apparent coarseness of the sample. So again, this metric matches well with what we're seeing visually. And then again, we have the cell size data next to the color and gloss data. And again, we can see that gloss and color measurement cannot properly differentiate between these samples, but the cell size measurements do a pretty effective job of it. It should be noted that highly reflected samples, meaning those with an average reflectivity value of greater than 2,500, are not suitable for 2D reflectivity measurements. 2D reflectivity measurements are really meant more for matte coatings than for glossy coatings. And so the Coarse paint algorithm, which is designed for highly reflecting coatings, does not include the reflectivity measurements. And so this is one of the main differences between the Leatherlike and the Coarse paint algorithms. All right, Coarse paint algorithm check, Leatherlike algorithm check. Let's now take a look at the fine algorithm, which is meant for both textured paints as well as some textured plastic parts. So here again, we have several samples that look somewhat different from each other. And here the main distinguishing feature, if you look closely, seems to be the relative roughness. So in order to measure what we see, as we like to do, we're now interested in determining the micro-mean peak distance as well as the micro-mean local amplitude of these surfaces. So for fine textures like this, there aren't really defined cells like we see with the Leatherlike or the Coarse paint algorithms. So if we look at this image to the right, the 3D topography image, we see that the individual light and dark sections are much, much smaller. It's kind of chaotic. And so the whole watershed segmentation thing doesn't really work here. So we need to come up with a different way to analyze this topography. And the way we do that is to calculate local maxima and minima, which here we can see in the extrema visualization image where the red dots represent the high points and the blue dots represent the low points. And the peak distance is the distance between neighboring local maxima. And the micro-mean peak distance is, of course, the average of all those values. And the local amplitude is the height difference between a maximum and the closest neighboring minimum. And of course, the micro-mean local amplitude is the average of all local amplitudes. So for this algorithm, we've ditched the whole idea of cells because they don't really make sense for this type of surface. And so we only focus on the local maxima and minima points. And here we have the micro-mean peak distance and the micro-mean local amplitude of each of these three samples. We can see that as the micro-mean peak distance increases, so too does the rough appearance of the surface. So higher peak distance correlates to a rougher appearance, and that also tends to correlate to higher local amplitudes, which also correlate to a rougher look. And here again, we have a table showing the set of measured values that we get when using the fine algorithm. So we have the micro-mean peak distance as well as the micro-mean local amplitude. And again, this is a perceived amplitude, so the color of the sample is going to affect these values in the same way we saw with those different colored samples when we were talking about the Leatherlike algorithm. And of course, we have the color and gloss values in addition to those 2D and 3D scales. So we have the Leatherlike algorithm for Leatherlike structures. We have the Coarse paint algorithm for high gloss textured paint. And we have the fine algorithm for fine textures like fine textured paints and plastics, as you can see here with this, this keyboard to the top right. And there are possibly more to come. We're always working on developing more. So if you have a product that maybe doesn't fit perfectly into one of these categories, but you want to be able to measure the structure of your product, I encourage you to still reach out to us. We'd love to take some measurements of your products, either by you sending us some samples, or if you're accepting visitors, at some point maybe we could visit you and take some measurements, and we still might be able to get some effective measurements out of this instrument. So to sum up, our overall visual perception combines color, gloss, and surface topography. And so in order to fully and accurately evaluate and control for the look of a surface, we need to be able to quantify all of these things. And that's why this instrument comes with 45-0 color, 60-degree specular gloss, which are both traditional measurements, but also these new techniques, the 2D reflectivity and the 3D topography, specifically for quantifying the texture of the surface. So that's it for the technical portion of our presentation. Now I'd like to just discuss a few of the new features in this instrument. So it does come with a large color touchscreen, a 3.5-inch screen, and it's sort of designed to be operated sort of like a smartphone. So it has this icon-based menu, very, very easy to use, very intuitive. It also has a full color screen, so you can get colorful data tables and graphical functions in the right on the instrument screen as well. And we also have a live preview camera, one of my personal favorite new features in our latest line of instruments. And so this is a camera that actually looks directly down through the aperture opening so that you can position the aperture perfectly on whatever you're trying to measure. So if you have a surface you're trying to measure that maybe has some scratching on it or some marring that you want to avoid, or maybe you're measuring a small sample and you want to make sure that that sample is perfectly centered under the aperture opening, this preview camera can allow you to see exactly what you're measuring so that you can perfectly position your instrument to your profiler for measurement. This also allows for digital standards. Digital standards provide for one binding reference. This minimizes error sources because electronic or digital instrument standards take the place of certified master standards, and only instruments with excellent accuracy between instruments allow usage of digital standards. So traditionally, the way things tend to be done when you have a large supply chain is that some headquarters location will come up with a master standard and then produce a bunch of working standards to send out to their various plants and suppliers to work on. But the inherent problem with that is that each of those standards is, of course, going to differ from each other. So already you're working different plants that are supposed to be producing the same material or the same products that look the same. They're already working off of standards that are slightly different from each other. So that's an additional source of error that you don't need. And the digital standards solve that issue where you just have one master standard measured by one instrument. That standard is distributed electronically to everyone who needs it. And then every plant, every supplier, every instrument is working off of the same target values rather than each have their own working standards. And so in order to do this, you really do have to have an instrument with very tight reproducibility, very tight inter-instrument agreement. All of the instruments have to measure very, very close to each other to allow for the usage of digital standards. And so this instrument, the profiler, does have excellent reproducibility to allow for that. And so, of course, we're not just going to say that without proving it. So in order to measure the inter-instrument agreement for the color measurement, different instruments were used to measure a set of BCRA tiles. And here you can see the range of the BCRA tiles. And so all four quadrants of the AB plane are covered. So you're getting all different hues of color that we tested against, as well as the full range of lightness from dark to light colors. And so here you can see those values. So these are color measurements of a pale gray, mid gray, and dark gray color, all achromatic colors. And so here in this graph, you can see that the red circle is the tolerance as defined by delta E 94. And then the little green circle inside of it represents 1/9 of that tolerance. And you can see that the measurements taken with different profiler instruments agree with each other very, very well. Those LAB points are pretty much right on top of each other. So all these different instruments are measuring these colors very, very closely. And if we look at these chromatic colors, we have a red, we have a green, we have a blue. We can see the same thing here. We have the tolerance, the red ellipse is the tolerance defined by delta E94. The green ellipse is 1/9 of that tolerance, and you can see these measured color values fall well within the 1/9 of that tolerance. So the agreement between these different instruments is very, very tight. And then here we have the agreement for the gloss values, which is also very, very tight. If you're familiar with Bic Gardner, you're probably familiar with our gloss meters, our micro gloss meters, and you probably know that they have excellent performance. And of course, this instrument is going to provide the same excellent performance, the same tight agreement and reproducibility as our standalone gloss meters. And then here we have the agreement for the structure values, the 2D and 3D parameters. So you can expect the cell size measurements to agree with each other to within 5% using different instruments, as well as the mean reflectivity. Those will also agree to within 5% of the measured value, and the reproducibility for the mean cell amplitude is 1%. Each of these instruments, as with most of our instruments, come with the Smart Chart software. And with that, you get the option to use either Smart Lab or Smart Process. Smart Lab provides for online measurement as well as memory transfer, color analysis with various graphical functions. You can get 60-degree gloss analysis with line graphs. And of course, that grain analysis with all those scales we discussed, as well as the images themselves. You can actually download and see the actual images that the instrument is taking and has analyzed to come up with these 2D and 3D scales. And then we have Smart Process, which is excellent for standardized QC processes. And so we have the organizer function, which allows you to define not only the measurement procedure as far as, if you're measuring a large part and you need to measure different parts, different areas of this part, whether it's, an automobile or an appliance or whatever, you can define check zones so that the operator knows exactly where to measure and in what order. And then you can also apply certain parameters to the readings. You can define the standards. So it makes it very, very easy to do regular QC work that you're going to be doing on a daily or weekly basis. It also has the ability to store large amounts of data and to easily filter that data based on those parameters that you've set. So it makes it very, very easy once you've accumulated large sets of data over a long period of time. You can evaluate that data in a huge number of ways. It's very, very customizable. So very good for long-term QC work. And so typically we say that Smart Lab is good for laboratories and R&D facilities, and Smart Process is good for production plants that would be doing regular QC work. So if there are any questions we haven't answered today or that I haven't answered by the end of our Q&A session, or if you'd just like to discuss your application with us personally, we encourage you to reach out to us, technical service team for Bic Gardner, including those of us here in the U.S., as well as our colleagues over at our German headquarters. And here we have each of our individual contact info here, including mine, Corey Cohen here at the bottom. That's me if you want to reach out to me. So feel free. We'd love to talk with you. We'd love to answer any additional questions you may have and possibly test some samples for us if you're interested and learning more about our measurements and what we can do for you. Just some quick announcements before we finish up. Our next web seminar will be next month towards the end of April, and that will be on gloss in theory and in practice, and that will include a live demonstration of our smart chart software. We do, once we are able to travel again, we do like to perform on-site seminars for you. So if you'd like us to come to your location, we can customize a presentation specifically to suit your needs. You can hear about whatever theory or instruments that you think may be beneficial to you. We can also bring our instruments with us so you can actually touch them and feel them and hug them and use them and see how they actually work in real life. We do have a new website, byk-instruments.com. Check it out. And we do have some videos of our instruments in action on YouTube. You can find them at youtube.com/user/BIC-video, or maybe just type BIC into your search bar. I'm sure you'll find it that way too. And last but not least, we encourage you, if you'd like to come visit us. So at the top there, you can see our headquarters and main production facility in Geretsried, Germany. It's a lovely place in southern Bavaria, right near the Alps, lots of beautiful countryside. So if you happen to be in the area or would care to visit, my German colleagues would love to host you there. They can show you around the facilities. Also, they have excellent beer in Germany. I highly recommend trying some of that out while you're there. And then at the bottom left, you can see our North American headquarters located in Columbia, Maryland. We're located right between Baltimore and Washington, D.C., also not too far from the coast. So plenty to do where we are as well. And of course, we do love our Maryland blue crabs. So I would encourage you, if you visit us, to try some of them out when you're here, particularly in crab cake form. I promise you every restaurant in Baltimore serves the best crab cake you've ever had. And we have beer as well, so come try our Maryland beer as well. So that is all I have for you today as far as the presentation goes, and I will now turn to the chat box and see if I can't answer a few questions. Have you used this instrument to characterize coatings that have been applied with a roller? I'm not sure, but we would love to. So if you care to send us some samples, if you're able to send us some samples, we'd love to take some measurements for you. If that's not possible, please reach out to us. We can possibly have one of our reps visit you at some point with an instrument and see if these measurements might be beneficial to you. Okay, this is a hefty question. How does this differentiate from the orange peel determination technology? So that would be our Wavescan instrument. Okay, so for one thing, the Wavescan is meant for relatively smooth surfaces. It's basically meant for automotive exterior surfaces. It's also used on things like boats, planes, appliances, sometimes plastic films. But the Wavescan is really meant for relatively smooth surfaces where you're going to see that orange peel, you're going to see the structure in the reflected image off of the glossy surface, but it's not really something you're going to be able to feel in the way that you can with like the coarse paint or the fine textured paint or the leather-like materials. And also the Wavescan, the orange peel meter, only works for very high gloss surfaces with low diffusion. So it really is, I don't want to call it a niche instrument, but it has specific requirements for being able to use that instrument, whereas the profiler can be used on sort of a different range of materials, particularly more heavily structured and lower gloss materials. And just to talk a little bit about the measurement principle behind the two, the Wavescan uses a laser measurement principle. So there's a laser light that's shined on the surface, and as you roll, it's actually a moving instrument. It moves during measurement. So as you roll the Wavescan across the surface, the Wavescan is measuring the deviation of that laser light, the small deviations of the reflection of that light. So it's a much different measurement technique than the profiler uses. And so no, we probably will not see that with both measurement techniques in one instrument. They're just too different. Okay, so we have someone asking about would this instrument be able to measure selectively sanded metal trim surfaces as well as real wood surfaces? Hard to say. Again, I hate to keep saying this, but please, I encourage you to reach out to us, and we'd love to measure some samples to see if that would work for you and see if that would work for ourselves. Does gloss affect A and B values? That's a good question. So because this instrument has a built-in 45-0 spectrophotometer, the answer is yes. Gloss does affect the way we see colors. Typically, glossier surfaces are seen as being darker and more chromatic. And so the 45-0 spectros measure color as we see it. So the spectrum is going to measure glossier surfaces as being darker. In the case of chromatic colors, more chromatic. So the A and B values will be measured as being higher or more negative for glossier surfaces than for matte surfaces. Okay, how can you establish a delta E tolerance having an issue that one part is within a delta E less than 1, but it is on the plus A side and the other is on the minus A side? Yeah. Okay, so this is an issue when you're talking about having multi-component parts that are produced separately, measured separately, and then put together because you can have, you have a standard and you have a tolerance, and both parts might measure within tolerance relative to that standard, but if you compare the parts to each other directly, they'll be out of tolerance. And this is something that we call panel match, or this is a feature we have when using our organizers, our smart chart software called panel match, where you can actually compare readings not only with between a sample and a standard, but between different neighboring samples, different neighboring panels, to make sure that those are within tolerance. Those are going to look good next to each other as well. So yes, this is an issue with multi-component products, but we do have a way to compare those to make sure they match as well. So if you care to reach out to us, I can tell you a little bit more about that and how that works in our software. When using digital standards, are there ever issues if different plants, suppliers, et cetera, would be utilizing different tints in the coding where the readings would show different spectral curves, metamerism, et cetera? So I believe by different tints, you're saying different colorants or different pigments that might have different spectral curves. So yes, that always is a concern, particularly, again, with multi-component products. Real quick, it is possible for different colors to have different spectral curves, but the same or very similar LAB values under a given illuminant. But when two colors match under one illuminant but not under another, that's referred to as metamerism, which is what you're asking about here. So yes, metamerism is an issue, and that is something you can have an issue with when dealing with different suppliers. But generally when a supplier or when a headquarters location sends out standards, they specify the illuminant to measure it under. So if all plants, all suppliers are measuring under the same illuminant, even when you're dealing with metamerism or different spectral curves, those colors could still match under the given illuminant. And so it really comes down to just making sure that you're choosing the correct illuminant for the application, because two colors may match really well under sunlight, but not under interior lighting. And so if it's a product that's typically used outdoors, like an automobile, you always want to measure the color under, say, D65, so that you know those colors are going to match under daylight. If it's an interior product, like, I don't know, a textile or something, interior wall paint, you might want to measure under fluorescent lighting or incandescent lighting, or maybe look at a few different ones to see whether there is metamerism. And there actually is a metamerism index calculation that you can get with this instrument, with the software, that will tell you how different a sampling standard or two different samples will look under different lighting conditions. Yes, we will be sending out a copy of this presentation to all attendees over the next few days. Okay, we have a question. Is there some correlation between D6510 and 450? So those are actually referring to different things. D65 is the illuminant, so that's a representation of the light source. So when you measure under D65, you're seeing what the color looks like under daylight, as opposed to, again, for example, the A illuminant is representative of incandescent lighting. There are F illuminants that represent fluorescent lighting. There are new illuminants coming out that represent LED lighting, so that's becoming more and more common. And the 10, D6510, that 10 refers to the observer function, and that has to do with actually the cones, the color cones in our eye and how we see color visually. So D65 is the illuminant. 10 is the observer function, which are used to calculate color values, whereas 450 is the physical geometry of a color measuring instrument. So 45 represents the angle of the light source, 45 degrees off the normal. 0 represents the detector normal to the surface at 0 degrees. And it looks like that is all the questions we have. And oh, look, it is now 11 o'clock. So I'll go ahead and wrap up this presentation. I want to thank all of you for attending. I hope this was beneficial to you. And seriously, if you have any additional questions or want to discuss your particular application, we'd love to hear from you. You have, or you will have all of our contact info when you get the presentation, so feel free to reach out. Thank you all, and I hope you have a good rest of your day and a good weekend.